What's up, guys? Probably the last video on energetics before I move on to the next topic, which will probably look at structure and bonding. This one looking at bond enthalpies, which you will have looked at GCSE probably, but will attack slightly differently A level. Before we get into it, like, subscribe, share, and if you've got any video requests, write them in the comments and I'll see what I can do. Let's get into it. So, bond enthalpies, for starters, let's have a look at the definition. So, it's basically the enthalpy change for to break 1 mole of covalent bonds in the gaseous state. And really, this is the reason why we didn't look at this in the sort of introduction to the topic, because it breaks away from that scaffold. But it's very, very important in terms of how we handle these questions. Let's sort of look at a bit of an example. So methane, propan-2-ol. So methane, you've got carbon. Carbon forms 4 covalent bonds. Meth means 1. The ane bit means it's saturated. So this is methane. And there we can see we've got 1, 2, 3, 4 carbon-hydrogen bonds. So we've got 4 lots of carbon-hydrogen bonds. And there we'd look at our data and we'd see that each of those is worth 412. So we do 4 times 412. Right, for propan-2-ol, pro means 3. So 1, 2, 3. 2-ol means we've got OH on that second hydrogen, second carbon, sorry. And the an tells us that it's saturated, so it's full of hydrogens. So here we could see we've got 2 lots of these. We've got 5 lots of carbon-hydrogen bonds. So 1, 2, 3, 4, 5, 6, 7, not 5, 7. Thank goodness I checked. 1 lot of carbon-oxygen. And 1 lot of oxygen to hydrogen. So again, for this, for all of the bond enthalpies, we'd look up the values, we'd multiply, so we'd do 2 lots of 348, 7 lots of 412, etc., etc. Now, again, like, this is why I think it's much easier to work with our displayed formula. I also want to make this point, is that where these are calculated, where we have this data, what happens is we take a load of compounds. So we take methane, ethane, propan-2-ol, loads and loads of these. And we'd look at the average bond enthalpy for these bonds. So the average for a CH bond, for example. And the reason I make that point is that the CH bond here is going to be slightly different to the CH bonds here. So overall values might be slightly different, but what we're doing is taking an average of carbon hydrogens. So it's enough for us to work with, but sometimes you're asked questions on why those values might differ from actual values, and that's our idea. So bond enthalpies, we can say average of a range of compounds. So true value may differ. Anyway, let's get into the calculations. So, calculate the enthalpy change for this reaction using the bond enthalpies given. So I do promote trying to draw the displayed formula first of all. And if you're unfamiliar with this, there'll be future topics that look at that. We've got Cl2, C2H5Cl, and HCl. Bond enthalpy, so again, to break 1 mole of covalent bonds in their gaseous states. And it's to make atoms, right? This is important. So what we've got is 2 lots of carbon gas, again, gaseous states, plus 6 lots of H gas, not H2, but H gas in this case, plus 2 lots of Cl gas, right? And now we can start working out what our values are. So we have 1 lot of CC, and we've got 1, 2, 3, 4, 5, 6 lots of CH, 1 lot of Cl. So we've got 1 lot of 3, 4, 8. We have 6 lots of 4, 12 for carbon hydrogen. And we've got 1 lot of ClCl 338. 338. We're trying to work out this. And then we've got 1 lot of carbon-carbon again, 348. We have 5 lots of carbon-hydrogen this time, so 5 lots of 412. 1 lot of carbon to chlorine, so 338. And 1 lot of HCl, 431. And again, think about, we're going this way. We can't go this way. We start here. We're trying to get to there. So we go this way. Initially, we're going with the arrow. So we don't need to do anything to those values there. So we've got 3, 4, 8 plus 6 lots of 412 plus 3, 3, 8. Now we're going against the arrow, so minus 3, 4, 8 plus 5 lots of 412 plus 3, 3, 8 plus 4, 3, 1. And there we get to minus 115 kilojoules per mole. Next. So again, let's draw these out in the first place. So calculate the CC bond enthalpy. So this is slightly different. We're trying to work out the CC enthalpy in this. We've got the enthalpy change for the reaction. Notice as well that this is a liquid. Our definition, remember, talks about gaseous states, and we're given our delta H for enthalpy there as well. So I'll write a little signal to myself. We've got a liquid here, okay? So we've got C2H5 OH plus 3 lots of O2 makes 2 lots of CO2 plus 3 lots of H2O. Right, now, again, we're coming this way. We're coming down to break these bonds. So first of all, we've got the CC is what we're trying to work out. We've also got our vaporization. That's why I've made this signal to myself. So plus 44. And now we can start worrying about the bonds. We don't need to worry about CC. We're trying to work that out. It's going to be slightly different to the value that we've got here. We've got 412. So we've got 1, 2, 3, 4, 5 carbon hydrogens. So 5 lots of 412. 1 lot of carbon oxygen, so 360. 1 lot of oxygen hydrogen. Where's that? 463. And then on to this, we've got 3 lots of that double bond O, 498. Nice. Next, we've been given this value, so minus 1015. And then we've got 2 lots of C double bond O times by 2, so that's 4 lots of C double bond O. 743. And we've got 2 lots of OH times by 3, so 6 lots of OH, 463. Okay, now, again, we're trying to work out this as a total, right? So we are going like so. Now, let's plug everything in. So we've got our CC, and I'll put everything else in brackets for now. So we've got plus 44, plus 5 lots of 412, plus 360, plus 463, plus 3 lots of 498. All in brackets, equals. And that will equal all of this, right? So initially we're going with the arrow here. So minus 1015. Here we're still going with the arrow. So plus 4 lots of 743. Plus 6 lots. Cool, I've copied that badly. What was C double bond O? 743. No, sorry, of OH. 463. Sorry for that. Now, again, look, we know how to rearrange equations. All we need to do is subtract all of this to move it over, right? So all we're doing is moving all of this over. And subtracting all of that, right? Yeah. And again, we plug all of that into our calculator and we get to plus 314 kilojoules per mole. Here's one for you to give a go. So let me zoom in, screenshot, give it a go. I'll answer it at the end of next video. For now, let's look back at this. So, standard combustion style question. Let's start off by copying our equation. It's got 3C plus 4H2 plus half O2 makes C3H7OH. And again, we've got combustion. So it's going to be burnt to make our carbon dioxide. So 3CO2 plus 4H2O. Don't worry about the oxygens here. Now we've got our values. So we've got 3 lots of carbon. So 3 lots of minus 393. We've got 4 lots of hydrogen. So 4 lots of minus 286. On the other side, we've got minus 2010. And this is our value that we're trying to work out. We're starting here, we're finishing here. We can't go this way, so we go this way. Initially, we go with the arrow, so don't need to change any signs there. 3 lots of minus 393, plus 4 lots of minus 286. Now we're going against the arrow. So here we're going against the arrow this way. So minus all of this stuff, 2010. And there we get to minus 316 kilojoules per mole. hope that's helpful. Hope that's helpful. Again, please subscribe, share with anyone you think might find this useful. And I'll see you next time. Happy revising, guys.